All right, welcome back for lecture 4 on this series on optimal transport. So just as a recap for where we're at, last time what we considered was the space of all probability measures with finite second moment. And we equipped it with this 2 Wasserstein distance coming from optimal transport. And the focus of last lecture was this space as a metric space. So having this being a metric space lets you like measure distances between probability measures, and then you can use this distance for all sorts of applications. Today's lecture, we're going to see that this space is actually much richer than just a metric space. In fact, it's almost a Riemannian manifold. Okay, so why is this important? Being a Riemannian manifold, this will allow us to develop this set of like calculus rules for manipulating probability measures with this geometric structure. It will allow you to write down dynamics on the space of probability measures. In some sense, like Riemannian manifold is kind of the minimal structure that you would want to like define gradients. So once you have this kind of structure, then you can talk about gradient flows on the Wasserstein space. So gradient flows provide a powerful perspective for designing algorithms now. Like you can use gradient flows to minimize functionals and tackle all sorts of problems. So this is definitely one of the most, I guess, like one of the areas of optimal transport that has garnered the most interest in recent years. So this will be kind of like a conceptual leap compared to the previous lecture. So we're just going to try to digest these concepts slowly. Yeah, but actually I'll be focusing more specifically on this space. So I added this extra subscript of AC. So the AC stands for absolutely continuous, which just means like I'm restricting to probability measures which have a density with respect to the Lebesgue measure. This will like avoid a lot of technicalities. In particular, we saw from Brenier's theorem that if you assume that your measures are absolutely continuous, then we can talk about the optimal transport map rather than a plan. And this map is given by the gradient of a convex function and so on. So we're really going to be working with this space. All right, so first of all, like if we think about this idea of Wasserstein space as a metric space, one way to, yes, question? You're right. Okay, so when you restrict to absolutely continuous measures, this will not be closed under the topology of W2, but that's fine because like Riemannian manifolds they don't have to be closed. Yeah, I guess maybe what's more important is that this space is going to be closed under geodesics. That's going to be the more natural notion of closure. Yeah. Okay, so back to this idea of like the Wasserstein space as a metric space. One way to think about what we did here was we kind of managed to lift the Euclidean metric up to the space of probability measures. So we lifted the Euclidean metric to the space of probability measures. Here's an example of an instantiation of this. If I compute the Wasserstein distance between a Dirac measure centered at x and a Dirac measure centered at y, then you can check that this is just the Euclidean distance between the points x and y. So in particular, this tells you that Euclidean space is isometrically embedded in the Wasserstein space. So you can kind of view this as like, okay, we have this like metric on our ground space. Now we managed to kind of extend this definition to give a distance between all probability measures. So in this sense, we're like lifting concepts from Euclidean space to probability measures. So today, what we want to do is go one level beyond, and we want to ask this question: how do we lift not just the metric, but how do we lift dynamics? Okay, so what do I mean by dynamics? Now I want to think about curves. So if I have a curve in Euclidean space, this is kind of a general notion of dynamics. For instance, like you can think of this as like a gradient flow of a function, or like whatever like dynamical system you have. Today, what we want to understand is how to look at curves of probability measures. Okay, so the question is like, how are we going to do this lifting? And there's actually some precedent from physics. There's this very nice analogy with fluid mechanics, which I'll try to emphasize today. And the nice thing about this subject of fluid mechanics is that there's actually two different perspectives on how to study the dynamics of fluids. They're called the Lagrangian perspective and the Eulerian perspective. And these two perspectives are complementary to each other. So I'll write Lagrangian here and Eulerian here. And somehow in my mind, like the relationship of these two perspectives in fluid mechanics is going to kind of be mirrored in how we're going to lift Euclidean picture to Wasserstein picture for dynamics. So what is the Lagrangian perspective? So the Lagrangian perspective, so let's say xt, well, like in our probabilistic language so far, we've been thinking of xt as a random variable with some probability law. But in the language of fluids, we're going to equivalently think of xt as just like a particle, like a particle within your fluid that's evolving over time. So the Lagrangian perspective, it emphasizes individual particle trajectories. So in particular, I could talk about how like xt, like a single particle, is evolving with time. And then I can also talk about the velocity of the particle, the time derivative of it, which I'll call like xt dot. And the Lagrangian picture of fluid mechanics is just trying to describe these quantities, like how do individual particle trajectories look like. So in contrast, the Eulerian perspective, it's going to try to look at the fluid as a whole through fields. And so here we have mu t. So in probabilistic language, we are thinking of mu t as a probability measure, or I'm going to abuse notation because I'm working with this space of absolutely continuous measures. Whenever I write mu t, I'm also going to abuse notation and also think of it like as its Lebesgue density. This is a common abuse of notation in this field. So yeah, we've been thinking of this as a probability density, but in the language of fluids, this is the mass density. In particular, when I evaluate mu t at a point x, this tells me at time t and at the spatial position x, what is like the density of the particles. Okay, so this kind of describes the entire collection of particles all at once. And similarly, in the Eulerian perspective, rather than looking at the velocity of an individual particle, we're going to look at the velocity vector field. So this is going to be denoted Vt. The velocity vector field is, well, it's a vector field. It assigns a vector to every point in space. It's a mapping from Rd to Rd. And this, okay, so I'll write velocity field. And so Vt at x, this is supposed to be describing the velocity of particles passing through the spatial position x at time t. Okay, so when we switch to a Lagrangian mindset, we're going to try to keep track of these quantities rather than individual particle trajectories. But these two points of view are complementary, and like given one, we can kind of go to the other and vice versa. Okay, so let's see, first of all, how you go from kind of this Eulerian picture to the Lagrangian picture. So in order to provide a Lagrangian description of what's happening from starting with this Eulerian data, basically I need to tell you like how the particle trajectories are evolving. And the way that I can do that is because I have this velocity vector field. So if I look at a particle trajectory xt, in order to specify its evolution, I just need to tell you its velocity, right? But the velocity of a particle is just going to be like the value of this velocity vector field evaluated at the current position of the particle, which is xt itself. Okay, so this, all I'm saying is like if I know this like Eulerian description, the velocity vector field, I can tell you what the particle trajectories look like. The particle trajectories look like integral curves of this family of like this time-varying family of vector fields. So this is an ordinary differential equation. Okay, but now I kind of want to understand, in some sense, the other way around. Which is like, suppose that I know that my particles are evolving according to like these dynamics, then in order to understand the Eulerian picture, I need to tell you how this mass density is evolving with time. So if I can understand how this mass density is evolving, then I will have specified like the evolution just in the Eulerian perspective. And so there's a really simple way to do this, summarized in this proposition. So suppose that my particle trajectories are evolving according to these like vector fields Vt. And let's suppose that mu t is describing the mass density, or also or equivalently like the probability density of this random variable if you want to think probabilistically. Then the evolution of mu t is given by the following equation: partial t mu t plus the divergence of mu t vt is equal to 0. So this is known as the continuity equation. It's called the continuity equation like from the physics standpoint. For instance, like if you integrate this equation in time, then the integral of the divergence is 0. This is the divergence theorem. And so this implies conservation of mass. But it also tells you more. It tells you like the full evolution of the density mu t. Okay, so let's just try to see why this is true. Basically, in order to show this, I just want to argue about the evolution of test functions along this trajectory. So let phi be some test function. So to understand the time derivative of mu t, it kind of suffices to understand the time derivative of the integrals of all these test functions along mu t. Okay, but in probabilistic language, we can just like switch back to the Lagrangian perspective. So this is the same thing as how do I know the evolution of the expectation of these test functions along these trajectories? And this we can just do via calculus. So this derivative is just the inner product of the gradient and the velocity of our particles. But I told you what the velocity of our particle trajectories are. It's given by this velocity vector field. Okay, so let me like rewrite this in terms of integrals. So first of all, when I compute the derivative of this integral, because phi doesn't depend on time, I can just push the derivative with respect to time inside. So I'm basically assuming I have enough regularity, so all these like exchanges of differentiation and integration make sense. So the integral of phi with respect to partial t mu t is the same thing as the integral, the time derivative of these integrals. And this shows that it's the same thing as the inner product of grad phi with the velocity vector field with respect to mu t. So now I want to use this to get information about what partial t mu t is. And so I would know that if I could just isolate phi by itself on this side of the equation. So the way that you do that is, as Yair mentioned yesterday, like it's amazing what you can do with just integration by parts. So we integrate by parts, and that's where you use the divergence theorem. And when you do that, you get a minus sign, you get phi, and then you get I'm basically pushing this gradient on the phi to everything else. So I get the divergence of mu t vt. Okay, and then this equation is supposed to hold for every test function phi. And so the only way that can happen is if like partial t mu t equals minus divergence of mu t vt, which is the continuity equation. Okay, so some technical note, like what do I mean by this equation being satisfied? Because like I haven't even told you that, for instance, that this divergence makes sense. Like mu t might not be differentiable. So I'm going to sweep most of these issues under the rug for today. So this lecture is going to be formal and also like an initiation into this field. So when I say formal, it's not a synonym for being rigorous. Formal means I'm concentrating more on the form of what I'm doing rather than on its content. So I'm not going to worry about like regularity issues. But like if you really want to interpret what this equation means, you should think more in terms of this equation for test functions. In other words, like this equation is true in the sense of like duality with test functions. And then that can be like the rigorous statement of this. Okay, any questions so far? Yes?
Having a discrete set of particles and making the number of points. I would think that in a given region you have many particles which could have different velocities in different directions.
Okay.
But here you assume that the velocity is a function of the position rather than having a conditional distribution.
Yeah.
Can you always reduce this or?
I mean, okay, if you're asking about the physics, like I'm not sure what the physical argument for this is. Maybe like you're looking at a point of space like so infinitesimally small that like all the fluids in that little region is going to travel in the same direction. You don't want to think about the velocity going too crazy. It's a good question, but yeah, I'm just going to assume that like at every point you're just moving in one direction. All right, so what does this show so far? Basically, like if I have any family of vector fields, Vt, and I specify that like these Vt's are governing my particle trajectories through like these integral curves, then I know how to write down the evolution of the density mu t. Now I'm going to somehow give you like a converse statement. So what is this converse statement? It says, okay, so this is the kind of idea, the rough intuition. Any nice enough evolution of densities can be described as a continuity equation. Okay, so nice enough. So technically this curve has to be like absolutely continuous, but basically like I don't want my curves to like jump or anything like that. So let's say I have like a nice smooth evolution of densities. Now what I'm saying is like no matter what the evolution of densities is, I can find vector fields Vt and interpret the evolution of these densities as coming from these like particle trajectories, evolving with these vector fields Vt. Okay, but before we make this idea more precise, there's an important issue to address though, which is there's a ton of like non-uniqueness in the choice of vector fields Vt that will give rise to this same evolution mu t. So in order to talk about like, interpreting this curve mu t in terms of velocity vector fields, I need to answer like the question of like what choice of vector fields Vt. So let me give an example to illustrate this. So let's say I have a constant curve where mu t is going to be the standard Gaussian. For every time t. Okay, so this is a constant curve in the space of probability measures. Now let me show you like two different velocity vector fields that will give rise to this same curve of measures. So for the first choice of velocity vector field is obvious, Vt is 0, because like if none of the particles are moving, then of course like my density will be constant. So this is like one particular choice of vector fields I could take. But another possible choice of vector fields I can take is the rotation vector field. That looks something like this. Okay, because like if my particles are evolving according to this vector field, they're just going to kind of like swirl around in circles. And we know that the Gaussian is rotationally invariant. So even if my particles are moving in this way, if I just look at the law of all the particles, then it's going to remain Gaussian for all time, right? So now, like, if you step back, I want to ask you the following question. Let's say you observe this curve of measures, this constant curve of measures, Gaussian at every time. So which explanation seems like more plausible to you? It's like what the particles are doing. Okay, if you say like rotation, then I kind of have led you astray because that's not supposed to be the right intuition. I guess like, okay, so like if you only see the entire population of particles and you don't see the individual particle trajectories, of course, like without further information, I can't say like what the particles are doing. But in the absence of such information, then maybe we want to seek the most parsimonious solution. And so like this rotation vector field, it's kind of saying that the particles are somehow like doing a lot of wasted movement. Like the particles didn't need to continue moving around in order to like give rise to this curve of measures. So I'm going to say like this second possibility has a lot of wasted movement. And this idea of like wasted movement is going to tie into like optimal transport, which is of course like the theme of this lecture series. So I really want to say like if we focus on vector fields that would give rise to mu-t but don't have this wasted movement, then I should really posit something more like the left. So this gives me kind of a physical principle for how to select the vector field Vt that will give rise to this motion. Okay, let me also add more generally. If I take any other vector field Wt, which satisfies this equation, divergence of mu-t Wt equals 0, then T maps to Vt plus Wt also solves the continuity equation. Okay, this is just, this is like actually the entire source of non-uniqueness. Like if I have these vector fields Wt that have 0 divergence when multiplied by mu-t, then like this doesn't contribute anything to the evolution of mu-t itself. It just like generates this swirling like you saw in this Gaussian picture. So I can add any of these vector fields to Vt and I will still solve the continuity equation. So this is why there's like a lot of non-uniqueness in the choice of vector fields Vt and why we need to have a criterion for selecting the right one. Okay, so this is going to be our idea. So among all candidates for the velocity vector field Vt, and what does it mean for Vt to be a candidate for describing the evolution? Well, in this setting, I want you to think of this curve of measures as being prescribed to you. Okay, so someone just gave me this curve of measures, and I want to try to understand like what's driving this evolution, right? So in order for Vt to kind of explain the dynamics of mu-t, then I need the continuity equation to be satisfied, which I can write as follows. Divergence of mu-t Vt has to be equal to minus partial t mu-t, where the right-hand side is like prescribed. So notice this is like a linear constraint on Vt. Okay, so among all the Vt's that satisfy this linear constraint, the way I will choose Vt is to minimize the kinetic energy in order to have like as little like wasted movement as possible. So what is the kinetic energy? The kinetic energy is just this quantity. And the reason why is like, remember this is supposed to be the square norm of the velocity. And then mu-t is supposed to be the mass density. And then hopefully, like you know enough physics that 1/2 times the velocity squared times the mass, this gives you the kinetic energy. So this integrand is the kinetic energy density, and then I have to integrate over all of space to get the total amount of kinetic energy. Okay, so this is the total amount of kinetic energy in this velocity vector field Vt, and I want to find the one that minimizes kinetic energy subject to explaining the evolution of my curve of measures. So now let's show that this actually is a good criterion. So this is the theorem. So for nice curves of measures, there is a unique choice of velocity vector fields minimizing the kinetic energy. Such that the continuity equation holds. In other words, like Vt like explains mu-t. And moreover, like this optimal choice of vector fields Vt, it's characterized by Vt being the gradient of some function. And no, I'm not saying like gradient of a convex function, which was Bernoulli's theorem. We'll see like why I'm talking about gradients of general functions here. But this is saying that like gradient vector fields are the ones that are minimizing the kinetic energy and are like not giving rise to this wasted movement. Okay, so let's kind of sketch why this should be true. So first of all, let me talk about uniqueness. Okay, uniqueness just follows from strict convexity. Okay, so remember, like, we're defining Vt as like some solution to a minimization problem. There's some linear constraint, but the important part is that this objective function, this is a strictly convex objective function. And so if you're strictly convex, the minimizer is unique. So that much is easy. Let's talk about why gradient vector fields are optimal. And the reason for this is basically like, let's think about the constraint that Vt has to satisfy. So this constraint, divergence of mu t Vt has to equal this. So I'm kind of just like going backwards from how we derived the continuity equation in the first place. But so this constraint is like completely equivalent to the original formulation I had in terms of test functions. In other words, I need gradient phi Vt integrated against mu t should be the time derivative of the integral of the test function for all functions phi. Okay, so this is just rewriting the constraint. It comes from the proof of the continuity equation. So now, like, if you look at what this constraint is saying, well, like, okay, the right-hand side is just like a constant, like the left-hand side is the real constraint. Vt is only like acting on gradients of functions in this equation. Okay, so, and remember, like the problem is I'm trying to minimize like the norm of Vt. So if you think about it, like Vt, if you think about like the span of all gradients of functions, like Vt might have some like component in the span of the gradients and might have some orthogonal part, right? But if you have a part that's orthogonal to all the gradients, it's not going to affect the constraint at all, but it will increase your norm. So it's never optimal to have a part of Vt that's like orthogonal to gradients of functions. In other words, like if I given any Vt that satisfies these constraints, if I orthogonally project Vt onto the space of gradients with respect to the mu t norm, I will just get another vector field that satisfies the same constraints but has smaller norm. Okay, so I can orthogonally project Vt onto gradients. Okay, so this tells us why the optimal vector field Vt has to be the gradient of a function. But let me kind of give you another explanation for why this should be true. Okay, so if you think about the connection between like minimizing the amount of movement in the kinetic energy and the optimal transport problem, you can show that this Vt, it's going to be a limit of the following quantity. I take the optimal transport map from mu t to like some small time delta later. I subtract the identity and divide by delta. You can show this. Okay, so like what I want to, like to find the optimal Vt, what I want to do is like I want to take mu t, I want to find the optimal transport to like a short time later, but then I subtract the identity to look at the displacement, and then I divide by delta, and then in the limit, this should give me like the velocity of this like kind of optimal transport. And if you remember, like this this transport map, this is the gradient of a convex function by Brennier's theorem. But I'm going to subtract the identity, which is the gradient of a function. So now this, because I've subtracted the identity, this is no longer the gradient of a convex function, but it's the gradient of some function. And this is preserved in the limit, so you can argue that Vt, through this reasoning, that Vt also has to be the gradient of a function. And like this also provides you a way to like argue about existence. Because like, why should there exist some Vt that explains these dynamics mu t? Well, this is like one way of constructing what this Vt should be. Right. Sure. Any questions so far? Yes.
You say the psi function not necessarily convex.
Yeah, psi is not necessarily convex.
From that argument.
So no, just this term is gradient of a convex function, but I'm subtracting identity, so it's no longer, the whole thing is no longer.
Can I just say that it's always a convex function minus identity?
But then that basically gives you gradients of like arbitrary functions.
Oh.
Yeah. Sort of, yeah. Well, it's a gradient vector field, and this kind of encodes the fact that it has no rotational component. Correct. Yeah, the curl of the gradient is 0. Yes. This is also basically like the Hodge theorem from differential geometry. All right. Okay. So what can we do with this? Now we're going to like try to interpret what's going on here in the language of geometry. So what I said is I could start off with any curve of measures mu t. I could find this nice choice of Vt. Now Vt like completely governs the evolution of mu t. I really want to think of Vt as telling me like in what direction, so to speak, is my curve mu t moving at time t. So we're going to think of Vt as the tangent vector to the curve at time t. So this is what it looks like. I have some curve mu t in Wasserstein space, and I want to think of like the velocity of this curve as being this vector field Vt. So that leads me to define what is the tangent space of Wasserstein space at mu. So we saw like these vector fields, they're just characterized as gradients of functions. So this is going to be all gradients of functions. And let's say that this is like smooth, compactly supported. And then I want to maybe like take the closure with respect to the L2 norm. So this will be the tangent space, basically like all gradients of functions. And I'm going to equip this tangent space with the norm. And the natural norm, of course, is L2 mu, because that's how I define this kinetic energy minimization problem. Okay, so this is the ingredients of a Riemannian manifold. So what is a Riemannian manifold? It's a space that looks like locally Euclidean in the sense that at every point I can associate to it like this vector space, the tangent space. The tangent space is supposed to tell me like all the possible directions I could start moving. And then each tangent space is equipped with a metric, like a Hilbert space inner product. So that's what I've done here. I've defined the tangent spaces and this like Hilbert space metric. So like technical caveats, the Wasserstein space is not like literally a Riemannian manifold. There's like technical difficulties in making this work, but basically like the the point of these lectures is that you can do like many of the calculations that you can on Riemannian manifolds over the Wasserstein space. And like the next lecture will like talk more about this calculus, like how to take gradients and so on. Okay, so let me just emphasize what I mean by tangent vector. So when I say that Vt is tangent to the curve at t, you should think of this statement as meaning two things. The first thing is that Vt should describe the evolution of μt in the sense that the continuity equation holds. That's the first requirement. And then the second thing is that Vt should actually belong to this tangent space, which morally is equivalent to like being the gradient of a function, equivalent to like minimizing kinetic energy. Okay, so these are like the two requirements to be the tangent curve, tangent vector to a curve. Let's see. Good. Yes. So you want to generalize beyond the quadratic cost for? Okay, so one natural generalization is like if you consider a Riemannian manifold and consider the space of probability measures over this Riemannian manifold, then you can kind of lift the Riemannian structure up to the space of probability measures. For general costs, though, there's like not really, yeah, you should maybe think of this procedure as like lifting the geometry of Euclidean space up. And so like, if you just have this general cost function, I don't think there's really a Riemannian structure underlying it. Yeah, and also like one thing is like, although we started off with Euclidean space, which is kind of like a trivial Riemannian manifold, it's like flat. We never need to talk about Riemannian manifolds when talking about Euclidean space. When we do this lifting, then the Wasserstein space is actually like a non-trivial manifold. It actually has like positive curvature. And then you really need this like Riemannian formalism. Okay, so far actually like this kind of doesn't have anything to do with the optimal transport. Like I kind of just, we did this as motivation, and then I kind of just defined this Riemannian structure over the space of probability measures, but how is this actually related to optimal transport? So that'll be the next thing we want to do. Okay, so let me say like formally, we have said that this space is a Riemannian manifold. So this interpretation is due to like Felix Otto. And now like, okay, so whenever you have a Riemannian manifold, then it induces a distance . So how does it induce a distance? Well, okay, let's say I have two measures, mu0, mu1. Then the way I can define a distance between mu0 and mu1 using this, using the ingredients of Riemannian geometry is as follows. I take the infimum of, okay, let me just write it here. Okay, let me write this as shorthand. So from now on, like when I write subscript mu, this is going to be the L2 norm with respect to mu. Okay, so this should be interpreted as like the norm of the tangent vector at the point mu. Okay, so this is the induced distance on a Riemannian manifold. So what is this saying? So this minimization is taking place over all curves that join mu0 and mu1, along with their associated tangent vectors. And this is like the magnitude of my velocity at every time. So when I integrate the magnitude of the velocity at all times, this is like the arc length of my curve. Okay, so what this is saying is like the distance between 2 points is like I looked at all curves joining these 2 points and I find the one that has the smallest arc length joining them. And then this like smallest possible arc length, this will be like what I call the distance between 2 points. Okay, so in general, like every Riemannian manifold has associated with it a distance function defined in this way. So it's another like variational problem. This variational problem though turns out to be like not the most like convenient analytically. And the reason why is that if you reparameterize a curve by like speeding it up, then like the value of this arc length is invariant. It doesn't change. So this problem, like if it has a solution, it will have many solutions, like obtained by all possible like time reparameterizations of the curve. So this is not like the ideal problem for ideal property of a variational problem. So instead, like usually what's more convenient to consider is this square, like so. So when you put squares here, instead of having the interpretation of arc length, we call it the energy of the curve. So there's only like one difference between this problem and the previous problem. The only difference is that the minimizers of this problem are like the minimizers of the arc length problem plus the additional constraint that the solutions have a constant speed. So this will be like convenient for us. So yeah, but in the end, it just is another way of like defining this induced distance. So now I want to ask like two questions. For this Riemannian structure on the Wasserstein space that I defined, well, what is the induced distance? And spoiler alert, it's going to be the Wasserstein distance, which is like connecting back to optimal transport. And then the second question is like, the solution to this variational problem is going to tell me what are the shortest paths between mu0 and mu1. So in Riemannian geometry, the shortest paths are geodesics, right? Not only are they geodesics, as I told you, because I put the squares here, they're going to be like constant speed geodesics. So by solving this variational problem, we'll be able to answer this question, which is what are the geodesics in Wasserstein space? Right, so here's going to be our theorem, is that, okay, if I just write down this variational problem, vt squared vt dt over all curves joining mu0 to mu1, then the value of this problem is exactly the Wasserstein distance between mu0 and mu1. So the induced distance from this Riemannian structure is the Wasserstein distance. In other words, like the Wasserstein space is not just a metric space, but like actually arises from a Riemannian structure. So in that sense, it's much richer. So this formula itself is like already pretty interesting. So it goes by the name of the Benamou-Bernier formula. And then the second part of this theorem is going to identify what are the minimizers. So the geodesics are given as follows. So let x0 drawn from mu0 and x1 drawn from mu1, let these random variables be optimally coupled for the Wasserstein distance. So first I draw an optimal coupling of the endpoints. Now I'm going to interpolate between these two random variables linearly. Okay, I just draw the straight line joining x0 to x1, and then xt is just the point on the straight line interpolation. And then mu t is going to be the law of this random variable. Okay, so I claim like this curve of measures mu t is the Wasserstein geodesic that joins mu0 to mu1. Okay, so by the way, so this is kind of called the dynamical formulation of optimal transport as opposed to what we've been doing so far, which is called the static formulation. So why static versus dynamic? Before, like when you give me the optimal transport map, it tells me like given any starting point x, then it gets mapped to t of x. So it just tells me the starting place and the ending place for a piece of dirt. But it doesn't tell me like how I should transport the mass from the start to the end. And this is the dynamical formulation, which tells me how I should transport from start to end. I should just traverse the straight line joining the start to the end. I mean, seems like natural enough. This also, of course, generalizes to manifolds, in which case, like, what you do is you first find the coupling, and then you follow the Riemannian geodesic joining the start to the end. Okay, so let's try to sketch the proof of this, and it's really not so bad. So let me just start with my objective function in this variational problem that I'm trying to minimize. Now, remember, like this squared norm of Vt under mu t, if I think back to what this is saying in the Lagrangian formulation, this is just the square norm of the velocity of my particle trajectories at time t. So here, like xt is from mu t, and then, yeah. So this is just going back to the Lagrangian framework, but then we can just now lower bound this by bringing the, I could lower bound this by bringing the norm outside. What am I doing? Expectation of the norm of the integral. Okay, this is a lower bound by bringing the norm outside, but the integral of xt dot by the fundamental theorem of calculus, this is just x1 minus x0. And then finally, because like xt is from mu t for all times t, x1 is drawn from mu1, x0 is drawn from mu0. So this is like some coupling of mu1 and mu0, but it may not be optimal. So it's always lower bounded by the Wasserstein distance between these two measures. And in this chain of inequalities, I used inequalities exactly twice. So now we can just examine what are the equality cases for these two inequalities. So first of all, this, of course, is obvious. So this is equality if x0, x1 are optimally coupled. And then this inequality, so this is like the equality case of Jensen's inequality. If you look at what that is, it will tell you that this is equality if and only if xt dot is constant. In other words, like my particles are traveling at like constant velocity. So the fact that your velocity is constant, this is equivalent to saying that you travel in a straight line. Traverse at constant speed. So that gives you like the form of these geodesics. Right.
So this also means that XT is an optimal coupling of
Yes, I think you can show that's true.
that comes after you have. I mean, you need first have the optimal coupling between X0 and then define XT. So the optimal coupling originally, if I understand correctly, between mu0 and mu1, and it doesn't involve T.
Yeah.
Yeah. So for every T, you are generating a coupling, and it turns out that
Yeah. Or like in other words, like if I define this whole family of random variables xt, then like all of these are simultaneously optimally coupled with each other. All right, so now let's just make a definition. So given two probability measures, mu0, mu1, in this space, the curve mu t, as in the theorem, is called, so this has like various names. It's called the displacement interpolation. Between mu0 and mu1. It's also called McCann's interpolation, after McCann, who suggested this. But from the geometric perspective, we're just going to call this the Wasserstein geodesic. Okay, let's see how I'm doing on time. Oh, am I out of time? Okay, I guess that's enough time for just one more definition. So we'll use this definition next time, but just to like give you an idea of what you can do with this interpolation, we're going to consider functionals over the Wasserstein space. So this is something that takes in a probability measure and outputs some possibly infinite number. We're going to say that this functional is alpha convex, like along the Wasserstein geodesics, if the following holds. For all t between 0 and 1, I want f at mu t to be bounded by 1 minus t times f of mu0 plus t times f at mu1 minus alpha t 1 minus t over 2 times the Wasserstein distance between mu0 and mu1. Okay, so this is just, and mu t here is like the geodesic joining mu0 and mu1. So the point is like, once you have this idea of like the geodesics on Wasserstein space, you can now define convexity by requiring your functional to be like convex along the geodesics of your space. And so like once you can use like convexity properties to prove like some pretty like powerful